So far, we have used Excel Solver to solve many interesting and important problems. However, there are many optimization problems where Solver's simplex LP and GRG nonlinear algorithms are unable to find optimal solutions. Fortunately, genetic algorithms often perform well on optimization problems where Solver's other algorithms perform poorly. The purpose of this chapter is to illustrate some interesting models that cannot be solved by simplex and GRG nonlinear algorithms, at least not easily or without tricks, but can be solved with genetic algorithms in a reasonably straightforward manner. In short, the methods in this chapter enable us to solve a much wider range of optimization problems. Beginning with version 2010, Excel includes the evolutionary algorithm, which was previously available only in Premium Solver. The following summarizes the three algorithms included with this newer version of Solver. They are Simplex LP Solver, GRG Nonlinear Solver, and Evolutionary Solver. Simplex LP Solver is used to solve linear models, including models where some or all of the decision variable cells are restricted to be binary or integer. GRG Nonlinear Solver is used to solve nonlinear models when the objective and constraints are smooth functions of the decision variables. Evolutionary Solver uses genetic algorithms to find good or close to optimal solutions to more difficult problems, including those where the objective or constraints are non-smooth functions of the decision variables. The first two solvers cannot handle models with if, max, min, and several other Excel functions. The problem is that such models often contain non-smooth functions in the objective or the constraints. Technically, a non-smooth function has discontinuities or points where its derivatives do not exist. It is sometimes possible to make these models linear so that the simplex LP solver can be used. But nonetheless, tricks are usually required to do so. Fortunately, this is not necessary with Evolutionary Solver. Evolutionary Solver uses a type of algorithm called a genetic algorithm, which is much more flexible. In the early 1970s, John Holland of the University of Michigan realized that many features in the theory of natural evolution, such as survival of the fittest and mutation, could be used to help solve difficult optimization problems. Because his methods were based on behavior observed in nature, Holland coined the term genetic algorithm. Simply stated, a genetic algorithm, GA, provides a method of intelligently searching an optimization model's feasible region for an optimal solution. Biological terminology is used to describe the algorithm. The objective function is called a fitness function, and the specification of values for all decision variables is called a chromosome. For most programs, a GA codes decision variables in binary notation. For example, 1001 represents 1 times 2 cubic plus 0 times 2 squared plus 0 times 2 to the power 1 plus 1 times 2 to the power of 0, which is equal to 9. Here, we use a simple example to provide a rough outline of how a GA might work. Suppose a company must decide how many units of each of two products to order. Because of quantity discounts, the function that represents total cost has discontinuities of the type observed in this figure. Actually, the total cost is even more complex than in this figure because there are two products, not just one. However, the only requirement of the algorithm is that total cost Tc as a function of Q1 and Q2 can be calculated for any combination of the ordered quantities Q1 and Q2. Suppose Q1 and Q2 must each be between 0 and 500. In this discussion, for simplicity, we assume that the model has no constraints other than lower bounds and upper bounds on each decision variable. Later, we'll discuss how a GA can handle other types of constraints. The genetic algorithms use the following steps. First, we're going to generate a population. The GA randomly samples values of the decision variables between the lower and upper bounds to generate a set of usually at least 50 chromosomes. The initial set of chromosomes is called the population. For example, two members of the population might be looking like this. Chromosome 1, Q1 is 100 and Q2 is 400. In binary form, Q1 is equal to 0011000100 and Q2 is equal to 11001000. Chromosome 2 is Q1 300 and Q2 200. In binary form, Q1 is 10010100 and Q2 is 01100100. Suppose in our example, chromosome 1 has a fitness value or total cost of $2,560 and chromosome 2 has a fitness value of $3,240. The initial population is constructed by randomly choosing points from the problem's feasible region. In our case, 9 binary digits are sufficient to represent any ordered quantity from 0 to 500. In step 2, we can create a new generation. Create a new generation of chromosomes in the hope of finding an improvement. In the new generation, chromosomes with a smaller fitness function in the minimization problem have a greater chance of surviving to the next generation. Recall that chromosome 1 has a fitness value of 2560 and chromosome 2 has a fitness value of 3240. Then chromosome 1 should have larger chance of surviving to the next generation. Crossover and mutation are typically used to generate chromosomes for the next generation. Let's look at crossover first. Crossover is very common. It splices together two chromosomes at a pre-specified point. For example, if chromosome 1 and 2 are combined by crossover and the crossover point is between the 4th and 5th digit from the right, the resulting chromosomes in binary form are as follows. New chromosome 1 is Q1 is equal to 1001 00100 and Q2 is 0110 00000. Equivalently, Q1 is 292 and Q2 is 192. A new chromosome 2 is as follows. Q1 is 0011 01100 and Q2 is 1100 11000. Equivalently, Q1 is 108 and Q2 is 408. Note that the two original Q1s are used to create the two new Q1s, and similarly for the Q2s. For example, Q1 for the new chromosome 1 splices together the left digits 1001 from Q1 of the original chromosome 2 and the right digit 00100 from Q1 of the original chromosome 1. Mutation is very rare. It randomly selects a digit and changes it from 0 to 1 or vice versa. For example, if the left digit of Q1 in chromosome 2 is mutated, the new Q1 in chromosome 2 becomes Q1 equals 0001 01100 or Q1 is equal to 44. As this example indicates, mutation can provide a dramatic effect leading to a completely different location in the feasible region. Therefore, an occasional mutation is useful for getting the algorithm unstuck. Step 3 is to determine when to stop the algorithm, called stopping condition. At each generation, the best value of the fitness function in the generation is recorded, and the algorithm repeats step 2. If no improvement in the best fitness value is observed after many consecutive generations, the genetic algorithm terminates. To handle a constraint such as Q1 plus Q2 less than or equal to 700, the GA adds in the minimization problem m times Q1 plus Q2 minus 700 to the fitness function, where m is a suitably large number such as 1 million. Now, any chromosome that violates the constraint has a high value of the fitness function because the penalty m times Q1 plus Q2 minus 700 greatly increases the value of the new fitness function. This causes the GA to avoid chromosomes that violate the constraint. If you let a genetic algorithm run long enough, it is guaranteed to find the solution to any optimization problem. The problem is that it may take too long before the GA finds the optimal solution. In general, you never know how long to run a GA. For the problems discussed in this chapter, an optimal solution is usually found fairly quickly, and some experimentation is necessary. So, you usually let Evolutionary Solver run for a while and report the best solution found. Unfortunately, you don't know if the best solution you have found is optimal, but it is usually a good solution, that is, close to being optimal. As a rule, GAs do very well in problems with few constraints, excluding bounds on decision variables. In addition, the complexity of the objective does not bother a GA. For example, a GA can easily handle min, max, if, and ABS functions in Excel models. This is the key advantage of GAs. On the other hand, GAs do not usually perform very well on problems that have many constraints. For example, simplex LP solver has no difficulty with multiple constraint linear models, but GAs perform much more slowly on those problems. Evolutionary Solver uses GAs to obtain good solutions. It begins with a population containing, say, 100 sets of values or chromosomes for the decision variables. For example, one chromosome might be 3.778 coded in binary form by the algorithm. This chromosome represents the value of X in this example, but it generally represents a set of values in the decision variables. Chromosomes that yield large objective values have more chance of surviving to the next generation of chromosomes. Chromosomes that yield small objective values have little chance of surviving to the next generation. Occasionally, Evolutionary Solver drastically changes or mutates the value of a decision variable. You usually stop Evolutionary Solver after a specified time period, such as 1 minute, or when there has been no improvement in the objective function for a given amount of time. Here's some general information about Evolutionary Solver. Evolutionary Solver usually finds a good solution, but there's no guarantee that it will be the optimal solution. Evolutionary Solver is not very efficient at handling constraints. The best way to handle constraints is to penalize a violation of a constraint. This is done by including a numeric penalty as part of the objective. Penalties are not used in this example, but they are illustrated later in this chapter. A good starting solution usually helps Evolutionary Solver in its search for an optimal solution. However, the starting solution is not absolutely critical to success. Evolutionary Solver places more of a burden on you to specify certain parameters of the algorithm. These parameters are specified in the Options dialog box, which we will discuss later. Unfortunately, these parameters are not very intuitive to most users, and some experimentation is necessary to find the best settings of these parameters for any given model. Nonetheless, if you use the default settings or the settings we suggest, they should work just fine. Much of the solution process is driven by random numbers that direct the search. As a result, two people can get different solutions to the same problem. In fact, running Evolutionary Solver a second time can possibly yield a different solution. You can set a random seed parameter to ensure the same solution on two successive runs. Optionally, after Evolutionary Solver has found a good solution, you can use GRG nonlinear solver to try to find a slightly better solution. If there's no improvement, you can probably infer that the solution found by Evolutionary Solver is optimal or close to optimal. In the next video, we'll use a simple example that is difficult for GRG nonlinear solver to demonstrate how to implement Evolutionary Solver.